CHP-J&J Engineering has been instructed to design and plan the construction for a solar umbrella structure at San Diego State University. CHP-J&J Engineering consists of 5 members: Chunyu Chan, Hawk Kao, Paolo DeRosa, James Panganiban, and Jared Skinner. The original specifications are as follows. Develop a design for a 150-foot by 150-foot solar umbrella to be placed in the center of Centennial Walkway, including details on materials and installation. After careful consideration, we found that Centennial Walkway is unsuitable for the installation of a solar umbrella structure that meets the design requirements. Other factors that influence this decision include the fact that Centennial Mall is considered a historical landmark on campus. Installation of a solar structure would create an aesthetic eyesore on an otherwise open and beautiful walkway under the San Diego sun. Also, the underlying utilities will also translate into a complex construction process. Therefore, we've decided to apply for a site location change. After careful consideration, we've narrowed the site alternatives to 2 parking lots. Parking lot A boasts about 70,000 square feet of area. Unfortunately, solar exposure is limited by the surrounding structures in the late afternoon. The other alternative selected is Parking Lot F. Parking Lot F can provide adequate area for construction at roughly 42,000 square feet, well over the 22,500 square foot requirement. Lot F also allows for better solar exposure for longer periods throughout the day. The request for a site change was approved Friday, February 4th. This change has been thoroughly documented throughout the design report. With a go-ahead on the site change, we begin our presentation with solar energy production. In the design of the solar energy grid, we first had to select a manufacturer to provide the panels. For this, we looked at Canica. Canica is a leader in thin-film solar technology. The panels selected are Canica's GEA060 60-watt solar panels. In terms of sustainability, this panel exceeds most because of its thin construction and conservative use of materials. The system is designed in support of Associated Students' Green Love initiative, striving for sustainability throughout our daily lives. Crystalline silicon PV modules lose some power generating capability with rises in temperatures, but amorphous silicon PV modules, like the GEA060, generate higher power during the summer and have superior light absorption per nominal watt power. These modules can deliver maximum performance during the summer months when electricity is needed most for air conditioners and other systems throughout the campus. Each string of panels will route the DC current through multiple combiners. For our combiners, we selected Midnight Solar's MNPV12. Each MNPV12 can support up to 12 inputs at high power. No secondary combiners will be required. From the combiners, the generated current is then transferred to the grid tie inverters. This system utilizes 3 Fronius CL power inverters capable of a nominal output of 44.4 kilowatts each. Fronius inverters offer comprehensive system monitoring, which is required of such large arrays. Fronius and Canica both recommend that the panels are strung in sets of 5 per maximum system voltage requirements. String divisions are calculated by hand as well as using Fronius' sizing tool to ensure optimum inverter efficiency. A total of 2,128 panels are designed to sit atop the steel frame. MC connectors allow the adjacent panels to be connected without extra wiring, which will help to limit the cost of extensions. Overall, the system has a nominal output of 128 kilowatts. The estimated panel recovery period is 3.5 years. And now we can go to structures.
Structural design. To begin the design process, we first must examine the specified design criteria. First, we want to maintain the prompt exposure area of 22,500 square feet. Taking into consideration the size of the structure, we would like to create it so that there's minimal impact to the location. Maintaining the site's original purpose is important, as it serves as a parking lot for faculty and staff. Finally, we wanted to design with future upgrades in mind. Next in the design process, we begin drafting multiple concept designs. From this point, we can adjust our design to better accommodate the physical restraints of the new site. After load calculations are complete, we then incorporate specific details to examine its constructability. We begin the design with several alternatives. First, a simple geometric draft. This concept is designed with the dimension of 150 by 150 feet, fulfilling the original design criteria. However, the equilateral feature of the design proves to be a challenge to fit in any of the listed locations. Therefore, we proceed to change the geometric aspects of the design. As we have discussed the location alternatives in previous sections, we have decided to change location. As a result of multiple considerations, we have concluded that the optimal location is parking lot F. As a result of this change, we have modified the original design, which is now concept structure 2. The arch design allows maximum amounts of solar panels to be installed. However, the shape of the structure limits its capacity to capture sunlight in maximum efficiency. Therefore, we have converted the circular surface into a hyperbolic surface. The surface allows longer sunlight exposure time for all panels, while maintaining a large number of solar panels. However, the structure's height exceeds the campus architect's guideline of permit requirements, which is the so-called Hardy Tower limit. Therefore, we have decided to lower the structure to a level surface. In order to reduce wind load, we have also included an exposed area to maintain normal air circulation. A 1/8 inch steel sheet is installed to create a universal mounting system that fits solar panels of all sizes. This allows future upgrades to the solar panels and prolong the structure's design life. With this structure in mind, we can proceed to the foundation design.
For the geotechnical design, we first start off with a boring request. On the request, the number of test samples, the spacing between the data, and the minimum depth of the sample must be stated. To get these values, some assumptions have to be made. These assumptions include the intended height of the structure, the total area of the structure, and the approximate loads. Below is a sample of our CPT data. The information given from the test includes the tip resistance, the sleeve friction, and the pore pressure, respectively. To the right are pictures of generic CPT equipment. Next, we graph the tip resistance, sleeve friction, pore pressure, and the friction ratio. To get the friction ratio, we divide the tip resistance by the sleeve friction. The horizontal lines running across the graph represent the different soil layers. After identifying the average magnitude of each layer, we use the classification graphs from the NCHRP synthesis to classify our soil layers. To the right is the actual illustration of the layers present under our site. 5 meters clay, everything below is sand, and finally, our water table is at 5 meters.
To determine the ultimate bearing capacity, the following parameters must be solved for: the cohesion, the effective vertical stress, the unit weight of the soil, coefficients that are dependent on the effective friction angle, and a design parameter based on the footing dimensions. A comparison between spread foundations, circular and square, mat and strip foundations were done. This was to select the most efficient foundation type. Our method was to determine the safe bearing capacity for each foundation, then to look at the corresponding volume of concrete. The spread foundation could support the structure with the least amount of concrete needed, saving money and construction time. The design of our foundation is per code. For this structure, there are 92 footings. The dimensions of each spread footing are as follows: a 4x4 foot base, 1.5 feet thick, with a 15 by 15 inch column atop the slab. To comply with code and maintain a practical design, 8 number 5 bars at 6 inches off center are applied, spanning in both directions of the base.
At this point, we can determine our method of construction.
The total construction costs consist of equipment cost, material cost, solar panel cost, and maintenance cost. The general cost. To the left are general requirements for construction. Listed to the right are the specifications of the general requirements. For example, the office trailer is 20 feet by 8 feet, rented per month, and we are anticipating on having the trailer for 3 months. Therefore, the cost for renting the trailer is as listed. Here we have the estimated total cost of the project, which is $820,000. With project management and engineering salaries, the grand total is estimated as just above $1 million.
Sectioning. To make our project more efficient, we have divided our site into 4 different sections. This way, when the project activities overlap, it is more manageable. Here we have an overview of our construction schedule. We will start our project on May 23rd and end on August 17th, which is right before the fall semester. We have 5 phases. Phase 1 is site preparation, such as removal of the light poles and fencing installation. Phase 2 is foundations, in which the soil is excavated, rebar is installed, and cement is poured into the footing and the column. Phase 3 deals with steel work. Steel columns are welded to guide frames. Phase 4 combines electrical wiring and roofing, which deal with wires and solar panel installation. And finally, Phase 5. It consists of paving and striping of the asphalt, electrical final trim, final punch-out, and cleaning. This concludes our construction section.
And now we can look at sustainability. Sustainability played a key role in design. The design of this structure most directly affects the teachers and faculty who use this lot daily. In order to design for practical usage, we wanted to maintain Parking Lot F's main purpose, and we'd like to keep this space designated for future faculty and staff. The structure will also provide protection for the cars below. Also, students will be able to admire the structure as Parking Lot F is used by many students as a route to the main campus from surrounding parking structures. As for the environmental impacts, there are very few. Solar energy production generates little to no pollution. Also, proper installation as well as disposal of old or malfunctioning panels is specified to be done in the proper manner as to minimize waste and energy. Plans for future upgrades, including charging stations for electric vehicles, can also help reduce harmful emissions. The estimated clean energy production of the structure is about 1.5 million conservatively for the next 25 years, although we estimate the life of the panels to be around 30 up to 40 years. Another economic benefit would be the solar incentives from regional energy providers. We thank you for watching and hope you've enjoyed our proposal.